Hello and welcome back to Differential Equation. We're starting Chapter 2, Introduction to, starting the Chapter 2 with 2.1, Introduction to Second Order Linear Equations. So first chapter was linear equations of the first order. Chapter 2 is going to be second order, and then Chapter 3 are going to be power series. Right? So, I know. Just putting that out there, so, you know, some calculus books should be flipped a little bit. So now, when we are talking about the second order linear differential equation, we are going to define second order linear differential equation by writing down the function, independent variable, the function, the first derivative, and the second derivative are all present. The most general case that you can put is going to be some function a of x times y double prime plus some other function b of x times y prime plus c of x times y equal to some forcing term on the other side. The forcing term could be something that is pushing the system periodically, like some kind of trig function. Could be an impulse function we call delta function, which is you punch the system once and set it into motion. Or it could be any type of function. So that forcing term on the other side, if it's not a zero, that's the one that sets everything in motion. It is important to note that you cannot have functions y prime, and y double prime. You can't have them squared. You can't have them in the cosine and sine because that would ruin linearity. This is the linear form. You can have whatever nonlinear functions within ax and bx and so on, but you cannot have y times y double prime. You cannot have, right? So in order for linearity to be there, you have to have y prime, double prime term, y prime term, and y without anything being done to that y or y prime or y double prime. They have to be single to the first power. So if equations are in this form, we would call them linear, maybe I write here, linear second order ODEs, ordinary differential equations. Now over here in blue I will say not linear, and I will write y double prime is equal to xy squared, right? So that's not linear because of the square. Y double prime plus y prime minus equal cosine x, right? This would be okay in every aspect, but those y and y prime are multiplied, and that breaks the linearity. The textbook has y prime squared and y cubed. All of these issues are there. So we are going to look into one more classification, and we really need this classification now. You remember me mentioning words homogeneous and non-homogeneous earlier, and I said that has to do with this being a zero or not a zero. We have to define that now because some of the methods that we are going to use will say particular solution, will say take the homogeneous part and do something and so on. You need to know what. Some people will say homogeneous, some people will say homogeneous. Potato, potato, right? No, let's have a debate, okay, and waste the rest of the class, all right? So the story, now in purple, the story of, I call it homogeneous and non-homogeneous. So homogeneous equation of the second order would be, say, 3y double prime minus cosine y, let's say, equal to, no cosine y, cosine x equal to 0. Bad example. Cosine x times y equals 0, much better. And then the same equation, non-homogeneous, would be 3y double prime minus cosine x times y is equal to, let's say, e to the x. All right. This example is sufficient for you to figure out the naming convention, right? Which one belongs to which. So if you have the forcing term, it's non-homogeneous, and if you have a 0, it's homogeneous. You must learn this classification.
So, the forcing term, non-homogeneous.
Good. Done. That's it.
Wait, say it again? You have a forcing term, non-homogeneous.
Good. If you have, let me circle it, if you have forcing term, non-homogeneous. If it's 0, it's homogeneous. Bueno? So technically the first equation we wrote as a general case of the second order differential equation is a non-homogeneous equation because it has f of x. If that f of x is 0, it becomes homogeneous equation. Now, what we're going to do now is we are going to divide the entire equation we started from. We're going to divide it by a of x. So I have a of x, y double prime, plus b of x, y prime, plus c of x, y equals to f of x. And I will divide everywhere by a of x. Now a of x cannot be 0, because if it was 0, we can't do it. And now we're just going to rename this as y double prime plus p of x y prime plus q of x y equals to lower case f of x, and this is going to be our equation. So now this is the second order, and obviously this is non-homogeneous. And the associated case, homogeneous case, would be just you have 0. Now, if you think about solving linear equation and then solving quadratic equation, when you solve linear equation 3x plus 5 equals 8, you have x equals one number. You have a single solution. You have a solution, unique solution, and you have one solution. If you go and solve x squared minus 100 equal 0, you know that you have to factor x minus 10x plus 10, and that gives you two solutions. They're unique, but it's two solutions. One is negative 10, one is positive 10. Same thing happens as you go for differential equation. You have the first order, you're expecting y equals blah, and that's what we had so far in chapter 1. Welcome to chapter 2. You will have y1 and you will have y2. You need to have two solutions. But there is a principle of superposition of solutions, and that means one solution is added to another. If one solution is the solution to if each one of the solutions is a solution to differential equation, then their linear combination is also solution to the differential equation. There is a proof for that. And we call this principle of superposition for homogeneous equations. And we write if the equation is homogeneous, linear equation, then you can work on the linear combination of two solutions. So this is very important. So for second order linear homogeneous ODE, ordinary differential equation, we have that the overall solution y of t is equal to c1 y1 plus c2 y2, where both of these y1 and y2 are function of x, and each one of those is a solution to the differential equation on its own. So this is the principle of superposition. And that is just a fancy name for us piling up the solution into one linear combination. The proof of this, if you're interested in proofs, is outlined on page 102. You have two constants now, C1 and C2. Each one of solutions is getting its own constant. And I think that's it for that part. Great. Existence and uniqueness theorem is still with us. That's always there. Existence says solution exists. Uniqueness says it's unique. Right? Remember how for x plus 3 equals to 5, you know that solution exists because it's 2, and you know it's unique. It's only 2 is the only solution. You don't have any others. The proofs for this would be the same, like for the previous section. You assume that it's not unique, and then you have two different ones. You plug everything in, and when you plug everything in, it works out that it's actually the same solution. So the proof is very easy. What you need to understand now is that initial conditions are going to be, again, two initial conditions, because you have to sort out C1 and C2. You have two constants to figure out. You better have two initial conditions. Now, those two initial conditions, generally one is given as y and the other one is given as y prime. And you use them in either the solution or the derivative of the solution. So initial conditions are now given as, and we write y of a is equal to b0 and y prime of a is equal to b1. So our initial conditions, one is on the function, one is on the derivative. Remember, now to check something, you have to find first and second derivative and plug everything in. Y of x or y of t, whatever, and plug them in the ODE. So to check, procedure is the same as usual. Nothing new, nothing special. So to illustrate this, I'm going to say that we have the differential equation y double prime minus 2y prime plus y equals to 0. Now we're not learning how to solve this. I am telling you what the solutions are. The first solution, y1, as a function of x, is e to the x. And the second solution, right, is x e to the x. So this is just given to you now. You will be learning how to obtain them on your own. We want to know if these are actually solutions and to write it as the single solution. So to solve this, I will first compile the superposition, which tells me that the overall solution y of t is going to be c1 e to the x plus c2 x e to the x. So this part over here is the superposition. Right, it's superposition. And now I would like to check if this is actually the solution. So I will find y prime. Y prime is c1 e to the x, stays the same, plus, so c2 x, so copy the first derivative of the second plus copy the second derivative of the first or third, or yeah, there we go. And now we have to do it again for the second derivative. So the derivative of the first one, you just get to copy it because you copy c1, and derivative e to the x is e to the x. Plus, and here's the product rule again. So copy the first derivative of the second plus copy the second derivative of the first. And then derivative of the other one stays the same. Everything stays the same. And now I'm going to color code this. You have your y double prime, you have your y prime, you have your y prime, and I ran out of these. Yeah. You have your y, you have your y. There we go. Plug in. Plug in and show that when you add them all up, they add to 0. If they add to 0, these solutions are correct. We get to box them. If they don't add to 0, something is wrong. We have to redo the problem.
So are we add all three of those?
Yep. Well, you have to, you're not adding, you have to use the signs, right? So you copy y double prime as is, combine the last two terms. So you have c1 e to the x plus c2 x e to the x plus 2c2 e to the x minus 2 times c1 e to the x plus c2x e to the x plus c2 e to the x. And then we have plus y, so plus c1 e to the x plus c2 x e to the x. And all of that should equal to 0. Is it? Well, sure it is, because if you look at these guys, they cancel. And then you have c2x e to the x and c2x to the x, and then you have 2 of these, so they cancel. And then 2c2 e to the x minus 2 c2 e to the x, they also cancel, and they all cancel, and we have 0 equals 0, and we conclude that life is beautiful. Can we conclude that from here?
0 equals 0?
Yeah. Or from the fact that you don't have to do it again. You can spin it in many ways. Oh, yes, you will. So we understand the concept of checking by plugging the values in. Right? Right. Good. The next concept is it's a definition, it's a concept of linear independence of two functions. Two functions defined on an open interval I are said to be linearly independent on I, provided that neither is a constant multiple of the other. In short, functions can be multiples of each other. Functions in question cannot be constant multiple of each other. That's it. Now, do I get to box this? And the answer is yes. Linear independence, it's going to be important for us when we run into repeated solutions. If you remember, sometimes when you solve quadratic equation, you get only one solution with multiplicity 2, right? So you solve differential. So you solve the ordinary, not that. You solve quadratic equation and you get x equals 3, x equals 3, right? It's easy to fix that. X squared minus 6x plus 9. So if you're solving equals 0. If you solve that equation, the x squared string that I gave you is going to compress back into x minus 3 squared. When you square root both sides, 0, square root of 0 is 0. You just have x minus 3 equals 0, x equals 3. So it looks like you only have one solution. You actually have one solution multiplicity 2, so there are two solutions there on the pile. Now, you get the same thing for differential equation. I can fix the problem so that your solution number 1 is e to the x and solution number 2 is e to the x. Are they linearly independent? Hell no, because e to the x times 1 is e to the x. So they're constant multiple of each other. And then you will have a procedure, and you will have what you do if that happens. You have to be able to recognize that. So functions are linearly independent. This is not the last time I'm going to say this in class about linear independence. We are going to see and use it a lot. So what you need to know now at this point is that two functions are linearly independent if they are not constant multiples of each other. And you also need to know that we need that eventually. And you also need to know that y1 and y2 cannot be linearly dependent. They must be independent. So you can't have them as a constant multiple of each other. The book gives you some examples, and you guys are so it is clear that the following pairs of functions are linearly independent on the entire real line. Okay, so examples of linearly, these are by no means all of them. There's just, I don't know, you have a sea of these and then you just scooped up 3 in a glass. That's it. So pairs of functions, examples of pairs of functions, examples of pairs of functions which are linearly independent. Sine x and cosine x, e to the x and e to the negative 2x, e to the x and x e to the x, x plus 1 and x squared, and then x and absolute value x, and then infinitely many after this. Sine and cosine are linearly independent because you cannot multiply either sine or a cosine by a number and get the other one. Linear independence means you're only allowed to multiply by a number, and if it doesn't work, right, then they're linearly independent. E to the x and negative e to the negative 2x should also be I can't talk anymore. Should also be clear, right, that they're not linearly independent, because even if that minus is not there, it doesn't matter, because this thing is equal to e to the negative x squared, right? And if you look at that, it's e to the negative x times e to the negative x. This is not a constant, right? So it's very simple to prove these kind of things. If you run into two functions and you're wondering if they are linearly independent or not, well, just try to make one to be the constant multiple of the other. If you're not able to do it, they're linearly independent. Anyone with me?
So you're able to do it, that's why they're...
Well, some are linearly dependent, and some are linearly independent. So if you can't find the constant to combine the two, they're definitely linearly independent. So we are going to have the general solution and the particular solution. Particular solution is there once you apply your conditions, right? So the same as linear order 1. Now, I want to know the test for linear independence. the test for that is Wronskian. It's the Wronskian now. With letters.
Really? I would never have guessed.
I know. Of course I'm going to write it. And he knows that, but he's going to ask, which is good. No, I'm serious. I'm going to write it now. Are you ready? He has W and K and everything. You're going to love it. Now, homework assignment. Write Wronskian and my last name 10 times. What? All right. Where's my K? There you go. Wronskian with W. I promised the W, right? And K. There they are. W and K. Look at that. All right. So the Wronskian is going to be the matrix which contains function, solution, and their derivatives. But what I'm going to say is, in general, we use the determinant of the Wronskian to check, and then we figure things out. So Wronskian works this way. The Wronskian is equal to the matrix F, G, F prime, G prime, and you work that out with the F, G prime minus F prime, G. So that's the Wronskian. And now, for our problems, for our stuff that we have to do, Wronskian is going to be tested between y1 and y2, and then y1 prime and y2 prime. So these are the ones, and then you have y1, y2 prime minus y1 prime, y2. So this is the test that you are going to unleash upon the two solutions that you have. And now, if the Wronskian is 0, they are dependent. If the Wronskian is not 0, they're independent. So, if Wronskian equals 0, right, we have the dependence, right? And if Wronskian is not 0, independence. There we go. So we said earlier that the solution y equal cosine x and y2 equals sine x are linearly independent. I want you to crank the Wronskian for this to check. Imagine how cool your life has to be so your name becomes a verb. Right? You Wronskian this thing. No, it's a power of people. You know that you have to populate derivatives underneath. You follow the formula. You know that the derivatives are going to the second row, and then you unleash the determinant for the 2 by 2.
That's just one.
0? That's the question. We don't care what we get. Question is it 0? If you get anything but 0, independent. If you get 0, dependent.
Not anymore, though. So
You all see the bride whose graves went from A to D minus. Wait. No, I'm serious. You ever tried to drive a cop?
I haven't had like been in that situation where I need to drive a cop.
How's it going? I see the gallery over there. I gotta take some pictures.
Okay.
We'll consult this. In the dark. I like this.
I'm gonna bring some of the fake cells out.
When you sing, I was on it. And then
Oh my god, it was sailing. It's like, ah.
sometimes I finish the word before you actually.
Yeah, that's right.
There's a reason why 300 pounds. I wear it. Derivatives go underneath, so cosine derivative is negative sine x, derivative of sine is cosine x, and then we... Guys, are you looking? Look at this. Whee! Yeah, because I'm nostalgic. I used to play the Wii Fit thing, and then one day told me I'm too fat to play. No, I'm serious. They actually have a pop-up for that because the board goes, I guess, I only up to 250 pounds.
Okay, well, did it say you're too fat, or did it just like...
No, it says you're too fat to play.
What?
Eat and you'll see.
I kind of want to try that now.
Okay, cosine squared.
I'll just like start jumping on it.
No, but I figured out if I sit on the couch and I just put my legs on it, it thinks I'm a 3-year-old. So I can actually play comfortably, and I'm better than all of them. So it's awesome. All right, are we done? With linear independence, yes. What do we have? So now we have the general solution to homogeneous equation. I'm going to put that in a box, and then we'll deal with the rest next class. So theorem 4, before you run out. General solution. Of homogeneous equations, we have y prime plus p of x, y double prime plus px, y prime plus qx, y equals 0. It's homogeneous case. Solution is going to be the y of x is equal to c1 y1 of x plus c2 y2 of x as that superposition thing we talked about. So now we know how to check, right, if y1 and y2 are linearly independent, and if they are, just line them up, add them there in a linear combination, and we are done. So we're going to take a look at these distinct real roots and repeated roots. Actually, no, I think that's actually... is that... Give me 1 second to go. Oh, yeah. So, you know, guys, I'm going to skip the last 2 theorems because that's what 2.3 is. The distinct real roots and the what. So, we'll do 2.2 next class. And see you in 2 days.